our Q&A session at the end. All right, thank you.
Great, thanks for that intro, and that's super helpful to know who's in the audience here, although we have a fairly intimate group. So my name is Sophia Wang, and I'm an assistant professor of ophthalmology at the Stanford Byers Eye Institute. And a major focus of my research group is using natural language processing, or NLP, on electronic health records in ophthalmology in order to understand and predict ophthalmology outcomes. So today I'll talk a little bit about a number of different approaches for using natural language processing in ophthalmology. And it's good the audience is 2/3 ophthalmology. So my talk is not extremely technical. It doesn't really presuppose that you know anything about natural language processing at all. So we'll take it from there. Okay. So just a little bit of an outline for what I'm going to talk about today. I'll start with a little background about natural language processing and electronic health records. I'll try and go over a few different methods of computing with words, including named entity recognition, neural word embeddings, contextual embeddings, and then I'll just end with a couple of conclusions. I do not have any conflicts of interest. Here are my disclosures. Okay. So I'm sure many of you have heard the oft quoted statistic that 80% of the world's data is unstructured. And so what does that mean? So structured data looks just like this, data you can put neatly into rows and columns in a database or Excel spreadsheet. Maybe it's numeric or categorical, but at the end of the day, its form in a database is relatively easily analyzable. Unstructured data is much less neat, doesn't necessarily fit easily into this format. There may be information that's very hard to extract, such as from text. And in our electronic health records, I can think of the information there as being kind of either structured or unstructured. So, the structured data might include those machine readable fields like all the billing codes, the patient demographics, even the medications to some degree, but there's a ton of information about patients that's just buried in the text, which is unstructured because it's not easily extractable. Everything in the notes might include of the patient, their disease history, family history, some details of their eye exam, their tests, their results of their tests, basically everything the doctor writes about them and their final diagnosis and treatment plan, right? So there's so much information there, but it's not easy to get out of the unstructured text. So what do the notes look like for ophthalmology? This is for our informatics folks here. So not long ago, our ophthalmology notes looked like this on paper, stacked in manila folders, essentially. But with a lot of electronic health records, now our notes look more like this. They're very dense, densely packed with a lot of sort of specialized information and specialized language and abbreviations. And sometimes it's hard even for other medical professionals who are not ophthalmologists to decipher these notes sometimes. But ideally, we'd like to be able to use all of this rich, unstructured text information to understand ophthalmology outcomes because, as a clinician, we're spending, so many hours every day writing these notes, right? So, the question is, how can we extract the human readable meaning from these notes into a computer readable format? Okay, so this is where natural language processing comes in, or NLP, which in this context does not stand for no light perception as it does in the ophthalmology field. So it's a branch of artificial intelligence, which is focused on understanding human language as it's spoken or written. And there are a lot of general and common applications of NLP, including, information extraction is one that I'll highlight, which is sort of recognizing some discrete piece or types of information out of a longer unstructured document, but also a lot of other things like question answering or machine translation, things that we use every day nowadays, even on our phones. But those are some general ways that natural language processing is used. I'll try and break down here what I think are the most common, but by no means exhaustive purposes to which we might want to use NLP techniques on notes from the electronic health records. So we might want to define a cohort. So this could be looking through notes for particular criteria to define a cohort, like if we're only looking for phakic patients, patients who have their natural lens, or only pseudophakic patients, meaning patients who've already had cataract surgery, or we could use this to define some kind of outcome, like did this patient have a particular complication or hemorrhage, something like that. And then after finding those things, we might want to do some kind of inferential study, find some specific risk factor and relate it to some particular outcome with the purpose of calculating some p-values or odds ratios. For example, a research question might be, are patients taking this drug Eliquis at high risk for suprachoroidal hemorrhage in glaucoma surgery? So you might need to use natural language processing to find all the mentions of this drug and all the mentions of the outcome, and then relate them with some kind of traditional regression, right? On the other hand, you might just be interested in making a prediction, like forecasting whether a patient will develop some outcome of interest, like, for example, will their vision get worse or better, or classification, which is very similar, not necessarily a longitudinal judgment, but maybe you want to say something about this particular piece of text. Is it an ophthalmology node or a neurology node or something like that? Right? So these top two kind of really focus on extracting specific pieces of meaning from the text, and sort of saying something very particular about those patients or those characteristics. So you have to be really careful to validate all the information that you're extracting using your automated algorithms, right? But the bottom two kind of focus on making an algorithm that performs really well, like, makes a prediction that's accurate. So to some degree, for these two, if you're using natural language processing, the algorithm doesn't necessarily need to figure out exactly what every word means in the note, so long as the final algorithm is accurate. So there's kind of two different ways of looking at things. But crucially, in order to do any of this, we have to turn the free text into numbers, essentially, that we can compute over, so we can run the regressions or build the predictive models and so forth. So there's a couple of approaches, which I'll talk about today, sort of progressing from simple to complex, and try to give a couple of examples related to ophthalmology. So the first approach is named entity recognition, really just using kind of word recognition, either in a very simple way or slightly more advanced way to just extract pieces of meaning out of text. And so named entity recognition, it's a natural language processing task, which is concerned with recognizing particular entities of interest. And they were called named entities because the original use case was recognizing names of people, places, and organizations. And in some ways, I think this approach most mimics how humans would think about extracting meaning from text. For medical text, of course, we aren't limited to people, places, and organizations. We might want to recognize diagnoses or treatments or medications, anything else that we particularly defined. So we can program our algorithm to recognize in a relatively simple way the presence of particular text or text patterns. So, for example, one of the first things I did when I got sort of access to our electronic health records was to evaluate cataract and glaucoma surgery operative notes. And we built a classifier to look at laterality of the surgery, meaning did it happen on the right eye or left eye? And this is very simple, just based on detection of words related to right or left, or OD or OS. And we built a classifier to figure out what kind of implant was used in the surgery, whether it was an intraocular lens implant or a glaucoma implant and what kind, and kind of accounting for all the different spellings and so forth, using basically like an advanced text searching method called regular expressions. And then validated all of this with manual annotation. So, this approach works pretty well if you have regular text like procedure notes or text that occurs in relatively predictable places and patterns. It also works pretty well for unique text, for example, like IOL models. If you see a text string that says SN60WF in an operative note, like there's no question or ambiguity about what that could be referring to. It's definitely some kind of lens model, right? So it doesn't really work that well for text that requires any sort of context to understand, like evaluating surrounding negation or history or references to the patient's family or things like that. So it's limited in that way, but it's a even so, you can get pretty far on just this kind of named entity recognition. So we use this method initially to look at glaucoma surgeries to define a cohort, and then almost instantly extract the details of over 700 glaucoma surgeries over 10 years, including all the different kinds of implants that were used and their differing success rates. And so it's kind of an example of using a simple text recognition-based named entity recognition to define a cohort and do like a very traditional inference study. Okay, so slightly more advanced named entity recognition, you can look at concepts and progress notes, and you really need more than just text recognition, because in progress notes, there's a lot of negation. People will write no diabetic retinopathy, or they'll write in history details like history of melanoma, status post-treatment, meaning they don't have it anymore. Or they might say some details about the family and not the patient, and they'll say mother has open-angle glaucoma, but not the patient, right? So in most cases, you're most interested in conditions that are about the patient and currently present and positive, right? So there are a whole host of generic toolkits that are available, and I've listed just a couple here, and they mostly specialize in extracting medications and medical problems and lab values, and they can handle some context, and they're usually built on very large biomedical dictionaries of terms. Right. But most of them were built and validated on general medicine notes. And these need customization and validation for ophthalmology terms, especially if you're planning to use them to really define a cohort or do inference studies, like I mentioned, get some kind of p-value for your risk factor that you detected. So we're kind of working on doing some of that customization and validation. And another big issue is for ophthalmology, most of these kinds of tools don't handle laterality out of the box, meaning right versus left eye. So any finding that it picks up, we wouldn't know which eye it belongs to, which is really important in our field. So here's a screenshot of part of a graphical user interface for one of these tools. And we've been working on kind of text recognition for ophthalmic medications, and then figuring out which eye they belong to, and so forth. Okay, so switching gears a little bit, the next approach I'll talk about is neural word embeddings. And this is a way to represent the meaning of all the words in your text as numeric vectors, rather than relying on the recognition of specific words or the presence of particular terms like we've been talking about so far. Okay, so this approach really gained steam about 10 years ago with the development of several algorithms that compute the numerical vectors used to represent words based on the context in which those words are used. So these word embedding algorithms, they position your vocabulary in kind of an abstract spatial dimension where words that appear or are used in similar contexts are close in distance to each other. So in that way, the vectors for the words captures the meaning of the word, because words close to each other in vector space are supposed to have similar meaning. And the way it's done is we train a model to predict a word from its context using a very large kind of training corpus or collection of words. And then the weights in the final trained model become the vector values of each word. So some interesting properties discovered about these word spaces is that words that have analogous relationships to each other, like man, woman, king, and queen, are situated a similar distance and direction from each other. So you can do math, simple vector math, on words to basically solve analogies and kind of recover relationships between words that capture gender differences, for example. So it's really interesting, the spatial geometry of the words contains these kind of linear substructures that can represent higher level concepts in our language. So the nice thing is you can download word vectors that are already pre-trained on a variety of corpora of text. They're mostly variations of Wikipedia or the general internet or books, and these are just sort of freely available. Right. So those are general domain word vectors, meaning they're trained on general English words, and they learn the numerical vectors for words based on how they're used in like Wikipedia, right? But the problem is that ophthalmology EHR notes are not really general English. There are a lot of informative and important words that are common in our notes that are not in general domain word vectors. And, I just like wrote a little example ophthalmology note here, and there's so many words here that are just like don't have a corresponding numerical vector because, they didn't appear in Wikipedia enough times in order to warrant, having its own vector, right? So huge sections of the notes wouldn't be covered by the embeddings. So to kind of mitigate this problem, we tried to train our own word embeddings using more ophthalmology domain-specific text. And this means we would create our own vector representations of words, including as many ophthalmology-specific words as possible by learning the meaning of those words from large corpora of text that use them in context. So we used, PubMed abstracts having to do with eyes and eye disease. And then we also tried using our own EHR notes, about 90,000 of those notes. And then we did kind of a very standard process to train our own word vectors, like 300 dimensional word vectors, which is pretty standard. Okay, and then we can visualize our own vector spaces for ophthalmology related words. So here you see some 2D projections of those vector spaces for 3 different clusters of words. I picked POAG, which is a glaucoma term, orbit for oculoplastics, and goutte for cornea, meaning 3 different kind of ophthalmic subspecialties. And I picked the 10 closest words in the vector space to these, and you can kind of see the separation, which is very gratifying. And then you can also see that the nearby words are indeed related. For example, next to in the glaucoma cluster, all of these abbreviations for different kinds of glaucoma. So that's kind of a nice like sanity check that what we did made sense. So there's different ways of doing formal evaluation of word vectors. And one of the ways is to basically have it complete analogies, right? We looked at the man, woman, king, queen analogy earlier. And so if you remember, vector math on the general embeddings can answer those questions or pick out the sort of missing 4th word in an analogy pair. So we developed sets of analogies that are related to ophthalmology clinical terms. So there's just a few examples here. And they're composed of word pairs that cover drugs and their sister drugs, anatomical structures, diseases and their locations, surgeries and their locations, and then some of the other relationships as well. And then, so, here's one example of an analogy visualized in embedding space. So we have OCP, which is a conjunctival disease, and its location, the conjunctiva, as well as pseudoexfoliation, a lens disease related to the lens. And the red herring random wrong word is neuritis. And so you can kind of see in our ophthalmology embeddings, these sort of check out as far as direction. And then for general embeddings, it sort of gets it wrong. And neuritis is like, not, picked as the wrong answer. So you can kind of, administer a test to the word embeddings and see how they do. So actually, the general embeddings did really well, better than I thought, but overall, I think it's a little bit better to include the ophthalmology domain-specific embeddings. So that's nice. Analogies are good, but we really wanted to test performance on an actual prediction task. So we tried to use the word embeddings to predict the visual prognosis of patients with low vision. So patients with low vision are, patients who have poor vision, who, aren't going to get better with glasses or treatment or surgery. And so we wanted to identify from the records those patients who would not be likely to recover quickly within a year, because those patients are the ones who might benefit from an early referral to rehab services to improve their quality of life, like learn how to use a cane or, get magnifiers and things like that. So we used our EHR database to isolate from our 4 million patients, all the 90,000 eye patients, and then we figured out which patients had at least one visit where the vision was low and worse than 20/40. And then of those who had at least 1 year follow-up, whether their vision got better or not. And so for our predictive model, what we did was we mapped all the words in each patient's notes, one at a time, to their corresponding 300-dimensional word embedding, using either our custom embeddings or just the general ones for a baseline comparison. And then we fed these into a deep neural network, several layers, including convolutional layers. And then finally, the model would output the prediction probability of whether the patient would still be worse than 20/40 after a year of follow-up, which was about 40% of the whole cohort. So those would be the patients that you might want to click early referral for rehab services. So here we show the performance of our algorithm, which, because it's a binary prediction algorithm, it's evaluated using receiver operating and precision recall curves. It's a pretty standard way of evaluating a classification task that discriminates between two outcomes. And so basically you want the area under the curve to be higher, so for the performance to be better. But, it's hard to judge, is this a good performance? We have areas under the curve of 0.83, which is kind of, decent. So you have to establish kind of a human baseline for that. So we also had an ophthalmologist, myself, review a sample of notes and then perform our own prediction of whether the patient's going to get better or not. And so we plotted that point here too for comparison. And so you can see it's actually not that easy to predict who's going to get better with treatment or surgery. And our ophthalmology embeddings, using those in our model, gives you a performance that's a little bit better than general embeddings. And then all the models do a lot better than the ophthalmologist. So we're doing something here that's of value, I think. Okay, so last kind of topic here. The final approach I do want to introduce is contextual embeddings. This is an approach that really came on the scene only a few years ago with the explosion in computing power and the ability to build very, very, very big neural networks. And some of the most famous of these language models have names: BERT, GPT-3, Elmo. And if you follow the news at all, you may have heard the splashy news about these kinds of models writing fake news articles. Here's an article written by GPT-3 to convince us that robots are not here to destroy humanity, or writing fake news, fake tweets, or writing movie scripts. Apparently, one of them wrote a movie script in the style of Federico Fellini, which someone actually made, impersonating celebrities and chatbots. Here's a chatbot which is impersonating Kanye West. Apparently you can text him and get sort of text generated in his style. This one is my favorite, which is using these models to produce code. You can turn a natural language query into a database query. So if you want to know something about users and their last payment or whatnot, you can don't have to write your own code to do that. So I think that's pretty exciting, right? So, without going into the very technical aspects of how the models are constructed, I'll just say that contextual embedding models can take into account, the context surrounding each word in a more sophisticated way. With neural word embeddings, every word has one vector, and it's supposed to represent that word's meaning, no matter what context it's in. And when we know that words have lots of different meanings depending on how they're used, right? So, this kind of model is more sophisticated. And it can also operate on units that are smaller than individual words, like on characters or subwords, so it can handle words that didn't originally appear in its training corpus. So anyways, as a result, obviously these models have become very powerful and have enabled a huge leap on many language tasks, and the most dramatic of which is natural language generation, right? But there are some disadvantages, including that the approaches are much more complicated, more computationally intense, requires more data, and there are still some limits to how much input we can give the models, how long a chunk of text we can feed to the model at once. And many of these models are available to use freely. Also, they're pre-trained on massive corpora of text. So BERT and most of its derivatives are trained on general English. just like the general word embeddings like Wikipedia and the internet and the books corpus. But there's also biomedical flavors of BERT. So there's BioBERT, which adds in training on PubMed articles and PMC articles to give it some medical background knowledge. And then there's also clinical BERT, which adds in some pre-training on ICU notes also to give it some sort of presumably, clinical context. So there's actually many other flavors of BERT now, and they all have their own kind of variations. So our research group is exploring how best to customize these language models for use in ophthalmology. And basically, you can use these pre-trained model weights as a starting point, and then fine-tune it to your own particular text, for example, ophthalmology EHR notes, and your own specific task, such as named entity recognition or prediction or something like that. So I'll give a more concrete example of using BERT for a task, for a named entity recognition task. So it might be like this. You say you want to recognize which parts of a note belong to the eye exam and which parts of the eye. So this might be really useful for finding patients' eye exams in long notes, and especially for notes from the VA, which are completely free text, or other kinds of free text notes. So what you can do is input your note, which is like a long string of text, into the BERT model, and then you want to get labeled output for every single word in the note, whether it belongs to the slit lamp of the right eye with the lids and lashes, or maybe it's the left eye and lids and lashes, or conjunct sclera, and so forth. And so you get like one prediction for every word. And to get output like this, though, we need input that is labeled like this so that the model can learn to emulate it. So in order to train BERT models, the bigger the corpus of notes, the better. And obviously, I'm not going to sit there and label tens of thousands of ophthalmology notes word by word in order to make a training corpus, right? So I wondered, can we do something smarter than that? So a little trick that we used was weak supervision. So instead of manually assembling a group of notes and labeling them all very accurately by hand, what we did was automatically assemble a group of notes with labels that are mostly about right. So in our EHR system, which is Epic, I'm not sure if you guys are using Epic. So we have these little boxes. They're called smart forms that the doctors can put little parts of the eye exam into, and it's labeled with each, what section of the eye exam it belongs to. And then the doctors, when they write the notes, they can import all that information into their actual note, where it shows up beautifully, usually in some kind of tabular format. And then what we see in the database end is just all the continuous stream of text, usually devoid of all formatting. But if we can consider the pairs of these notes and smart forms, which contain text that's essentially labeled, then we can use all the text in the smart forms to label the individual words in the notes. So it's not perfect, but at least this way we can get kind of 50,000 labeled notes very quickly, or relatively quickly, and start training a model. So when we evaluate the performance of our model against a sample of 100 notes from the test set that is actually humanly, manually annotated, then we see actually the performance is pretty good. Precision, which is positive predictive value, is uniformly very high, almost 1. That means that every word that the model picks up and labels is very likely to actually be a word that belongs to, the slit lamp, lids and lashes, or what have you. Recall, sensitivity is more variable. It kind of depends on which part of the eye exam we're looking at. So it kind of varies between 0.7-ish up to close to 1. So that means that it doesn't always pick up every word that belongs to that particular category. And there are a few limitations. If you use a totally independent set of notes, the recall drops, but the precision is still pretty good. And then there are certain situations that the model's just not built to handle yet, but I think it's a pretty good start. And we can also visualize what the model is predicting and making mistakes on with a few example notes. So I put in a few example snippets of notes, and everything in yellow is what the model is predicting. And then it sort of just skips words sometimes, which I boxed in red. So here for the lens on the right, it's supposed to be anterior chamber intraocular lens, and it only picks up chamber and lens, right? So, but almost everything that it does pick up is correct. So that's the high precision variable recall that you're seeing. So, what could we use a system like this for? This is pretty early research, but as I mentioned, we might use it to look for certain findings, maybe define cohorts based on certain eye exam features, or define risk factors for outcomes in inferential studies, or we could use it to generate features from the text for use in other predictive models. So any of those possibilities. Okay, so to kind of conclude, I want to point out or summarize some of the challenges for natural language processing for ophthalmology notes, which I've touched on today a little bit already. So, of course, laterality is a huge issue, right versus left eye. Dealing with the tabular formatting, especially with the eye exam, is an issue as well, a challenge. Our ophthalmology domain-specific vocabulary, requiring kind of customization of a lot of these models. Also, something I didn't really talk about is our notes are pretty choppy. They're not smooth paragraphs with real sentences like traditional dictations or, psych notes, for example. It's all very kind of short pieces and bullet points. So that can be a challenge as well. Many of our notes are very long, and many of the models have limitations to how much text you can put in at once. So that is another challenge. And then finally, I did talk about negation, history, and context. These are common challenges to almost all clinical named entity recognition systems. And so just a few concluding thoughts on the natural language processing. Circling back to this slide here, and what we've covered, we talked about defining cohorts of surgical patients, figuring out glaucoma surgery outcomes, doing inference studies here. These studies were based on very simple text recognition algorithms, regular expressions, and dictionary-based studies. We also talked a little bit about named entity recognition using BERT, which we could one day use to assist in any of these tasks. And we also covered examples of a few prediction algorithms, for example, predicting low vision prognosis. So that is the end of my quick whirlwind overview of natural language processing and ophthalmology, the work that we've been doing. So thanks so much for listening. Feel free to email me for any questions or check out our website. I will say the ophthalmology neural word embeddings that we created are available for download. So you can email me for details if you want to use those as well. And yeah, I'll answer any questions you might have.
Awesome. Thank you so much. That was an incredible talk. A lot of really exciting work